The Hessdalen Valley Lights. In the Hessdalen Valley in central Norway, about 120 kilometers south of Trondheim, researchers have documented a persistent geological electrical phenomenon for over 40 years. The valley experiences regular appearances of unexplained lights, luminous spheres and columns that appear in the air, sometimes lasting for over an hour, moving in patterns that seem to defy simple explanations. What makes Hessdalen relevant to our topic isn't the lights themselves, it's what researchers discovered about the rocks beneath them. Starting in 1983, scientists from Norwegian and Italian universities established a permanent monitoring station in the valley to study the phenomenon scientifically. In 2004, researchers led by Professor Erling Strand from Østfold University College began measuring electrical properties of the rocks and soil in areas where lights most frequently appeared. They found something extraordinary. Certain rock formations in the valley generate measurable electrical currents between 0.1 and 0.5 volts continuously. The rocks creating these currents are primarily sulfide-rich minerals embedded in the valley's bedrock. The Hessdalen Valley sits on geological formations containing significant deposits of iron and copper sulfides, along with zinc compounds. When these minerals are in contact with groundwater that has varying pH levels and mineral content, they create natural galvanic cells, essentially natural batteries. The mechanism is similar to the Baghdad battery discussed in the previous script, but occurring naturally on a geological scale. Different minerals, with different electrochemical properties, connected by moisture in the rock, create voltage differences that drive electrical current. But the Hessdalen rocks aren't just creating static voltage, they're generating current flows that can be measured moving through the ground. Research teams have placed electrodes at various points in the valley and detected currents flowing through the earth between different geological formations. In 2007, Italian physicist Massimo Teodorani published research suggesting that these natural telluric currents, earth currents, might be related to the light phenomena. His hypothesis proposes that under certain atmospheric conditions, the electrical currents in the rocks can interact with ionized air, creating plasma-like luminous effects. While this explanation remains controversial and isn't fully accepted, what's undeniable is that the rocks themselves generate measurable, constant electrical activity. Multiple research teams from different institutions have confirmed the phenomenon with independent measurements. What makes the Hessdalen rocks particularly interesting is the scale. This isn't a small laboratory curiosity, it's a geological feature extending across several square kilometers of valley floor and hillsides. The electrical generation is continuous, occurring 24/7, year-round, sustained by the natural chemical composition of the rocks and the groundwater flowing through them. Attempts to harness this electrical generation for practical use have been limited. The voltage and current levels are too low for significant power generation, and the distributed nature of the phenomenon makes collection difficult. But the existence of such natural electrical generation raises questions about how many other locations might have similar properties without having been detected or studied. The Hessdalen monitoring station continues to operate, with researchers from multiple universities maintaining equipment that tracks both the light phenomena and the underlying electrical properties of the rocks. The data is publicly available and shows clear, consistent electrical measurements from geological formations. Brazilian quartz deposits. In the state of Minas Gerais, Brazil, massive quartz crystal deposits have been known for centuries for their unusual properties. Beyond their size, some crystals weigh several tons. These formations exhibit piezoelectric effects of exceptional strength and consistency. Piezoelectricity is a well-understood phenomenon where certain crystalline materials generate electrical voltage when mechanical pressure is applied, and conversely, change shape when electrical voltage is applied to them. Quartz is the most common piezoelectric material and is used in countless modern devices from watches to radios. What makes the Brazilian quartz deposits unusual is that certain formations appear to generate continuous electrical potential without applied mechanical stress. In the 1980s, geophysicists studying the region detected persistent electrical fields around specific large crystal formations, voltage differences of 0.2–0.8 volts that remained constant over days and weeks of measurement. Initial theories suggested the voltage was caused by constant mechanical stress from geological shifting, the weight of overlying rock creating continuous pressure on the crystals, which would generate continuous piezoelectric response. But detailed analysis showed the voltage persisted even in crystals that were carefully excavated and placed in stress-free environments. Further investigation revealed a more complex mechanism. The quartz formations in this region contain numerous inclusions, tiny pockets of liquid and gas trapped when the crystals formed millions of years ago. These inclusions are under high internal pressure and create constant stress on the crystal matrix from inside, generating continuous piezoelectric voltage. But that's not the only mechanism at work. Some of the Brazilian quartz contains trace amounts of aluminum impurities that substitute for silicon in the crystal lattice. This creates defects in the crystal structure that can trap electrical charge, essentially creating natural capacitors within the stone. When these charge-trapping defects are combined with the natural radioactivity present in surrounding rocks, trace amounts of uranium and thorium in the granite formations, the quartz crystals can accumulate and maintain electrical charge over extended periods. The weak radioactive emissions ionize air or rock around the crystals, and the ions are attracted to and trapped in the crystal's defect sites, creating measurable voltage. Dr. Hartmut Schultz, a German geophysicist who studied the Brazilian formations in the 1990s, documented that some large crystals maintain voltage differences of up to 1 volt between different crystal faces continuously. For the 6 months his team monitored them. What makes these formations particularly remarkable is that the electrical generation is self-sustaining. The radioactive decay provides continuous energy input, albeit at very low levels. The crystal structure traps and maintains charge, and the piezoelectric properties allow the crystal to respond to environmental pressure changes. The result is a geological formation that acts like a very slow, very weak, but essentially permanent battery. Brazilian mineral prospectors have known for generations that certain crystal formations can affect compass readings and can create sparks when struck or rubbed. Whether ancient indigenous peoples noticed these electrical properties is unknown, but some researchers have speculated that certain crystals might have been valued specifically for these unusual characteristics. The Brazilian quartz deposits remain commercially valuable for industrial piezoelectric applications. Modern crystal growers can create synthetic quartz with more consistent properties, but natural Brazilian quartz is still valued for certain applications, where its complex internal structure provides advantages. Iron Mountain Telluric currents. In northern Sweden, near the city of Kiruna, lies one of the world's largest underground iron ore mines. The Kirunavaara mine has been in operation since 1898 and extends over 4 kilometers deep into the earth. Within this mine, researchers have documented powerful telluric currents, natural electrical currents flowing through the rock, that are far stronger than typical geological electrical activity. Telluric currents are known phenomena. They're electrical currents that flow through the Earth's crust, typically induced by variations in Earth's magnetic field or by electrochemical processes in rocks. Most telluric currents are weak, measured in millivolts over large distances. But in the Kiruna iron mine, electrical engineers have measured currents reaching several volts over distances of just tens of meters. These aren't temporary surges. They are persistent currents that flow constantly through specific rock formations, particularly those rich in magnetite, iron oxide. The mechanism involves several factors. Magnetite is semi-conducting. It can conduct electricity, but not as well as metals. When magnetite-rich rock is in contact with groundwater containing dissolved minerals, electrochemical reactions occur at the mineral-water interfaces, creating voltage differences. But the Kiruna mine's unusual strength of telluric currents appears to be amplified by its proximity to Earth's magnetic pole. Northern Sweden is close to the geomagnetic North Pole, where Earth's magnetic field lines enter the planet nearly vertically. This creates stronger magnetic field variations than in equatorial regions, and these variations induce stronger electrical currents in conductive rock formations. In 2003, mining engineers reported that some electrical equipment in deep portions of the mine was experiencing unexplained power fluctuations. Investigation revealed that natural telluric currents in the rock were strong enough to induce current in the mine's electrical infrastructure. Essentially, the rock was generating electricity that was interfering with the mine's power systems. Geophysicist Dr. Lars Erik Hjelt from the University of Oulu studied the Kiruna currents extensively and found that they followed predictable patterns correlated with variations in Earth's magnetic field. Solar storms and magnetic fluctuations cause corresponding changes in the telluric current strength, confirming the magnetic induction mechanism. What makes the Iron Mountain currents particularly significant is their strength and consistency. While telluric currents exist worldwide, the combination of iron-rich rock, proximity to the magnetic pole, and the presence of groundwater creates conditions where the electrical generation is powerful enough to be practically significant. Some researchers have explored whether similar geological conditions elsewhere in the world might produce harvestable electrical energy. The currents in magnetite-rich rocks near magnetic poles could theoretically be collected and used, though the engineering challenges of extracting useful power from distributed geological sources are substantial. The Kiruna mine continues to operate, and the telluric currents remain a documented phenomenon. Modern mining operations account for these natural electrical currents in their engineering designs, ensuring that electrical systems are properly insulated from the rock's electrical activity. The living stones of Costești. In the village of Costești, Romania, there are geological formations locally known as trovanți, or living stones. These are spherical or irregularly shaped rocks that appear to grow, move, and multiply, earning them the nickname living rocks. While the growth and movement aspects are geological processes that can be explained, what's less well known is that many trovanți exhibit unusual electrical properties. Trovanți are a type of concretion, sedimentary rocks formed by cementation of sand grains. They grow through a process where mineral-rich water deposits new material on the surface. After heavy rains, trovanți can visibly increase in size as dissolved minerals precipitate onto them. But in 2005, researchers from the University of Bucharest studying the trovanți discovered that many exhibit measurable electrical potential. The stones showed voltage differences between their surface and interior ranging from 0.1 to 0.4 volts, and these voltages varied in response to moisture levels. The electrical generation mechanism appears to involve the trovants's internal structure. Cross-sections of trovants reveal ring-like patterns similar to tree rings, representing periods of growth. These layers have varying mineral compositions and porosities, creating interfaces where electrochemical reactions can occur. When trovants are exposed to water, rainfall, or ground moisture, water penetrates into the porous structure through cracks and spaces. As water moves through the layers, it encounters different mineral compositions, some layers rich in calcium carbonate, others containing more silica, and some with iron compounds. These varying mineral compositions create galvanic cells at the interfaces. The trovants essentially become natural batteries when wet. The voltage they generate is weak, but measurable with standard instruments. The voltage decreases as the stones dry out, then increases again when they're re-wetted, a cycle that repeats continuously with rainfall and evaporation. Romanian researchers also found that trovants buried in soil show different electrical behavior than those exposed on the surface. Buried trovants in contact with humus-rich soil generated more consistent voltages, possibly because the organic acids in soil maintained chemical reactions at the mineral surfaces even during dry periods. What makes the Costești trovants particularly interesting for our topic is that they represent a class of living geological formations that generate electricity as part of their growth processes. The electrical generation isn't incidental. It's connected to the chemical reactions that cause the stones to grow. Some researchers have speculated whether ancient peoples might have noticed these electrical properties. Romania has rich folklore about trovants, with local legends describing them as stones with special powers. Whether these legends are based on observations of electrical phenomena is unknown, but the possibility exists. The trovants are now a protected geological monument, and some are displayed in the Trovanți Museum in Costești. Visitors can see the stones and learn about their unusual properties, though the electrical characteristics aren't typically demonstrated in public displays. Granite formations in Cornwall. In Cornwall, England, granite formations have been known since the 19th century to exhibit unusual electrical phenomena. Cornish granite contains high concentrations of uranium and thorium, naturally radioactive elements, along with significant deposits of tin and copper ores. This combination creates conditions for continuous electrical generation. The mechanism involves natural radioactivity. Uranium and thorium in the granite undergo radioactive decay, emitting alpha particles, helium nuclei, beta particles, electrons, and gamma rays. These emissions ionize the surrounding air and rock, creating free electrons and ions. When granite is wet, from rainfall, fog, or groundwater, the moisture provides a conductive path for these ions and electrons to move. The radioactive minerals act as a constant source of charge carriers, and the moisture allows current to flow. The result is measurable electrical currents in and around the granite formations. In the 1880s, when telegraph lines were being installed across Cornwall, engineers noticed unusual electrical signals on lines running near certain granite outcrops. Investigation revealed that the granite itself was inducing electrical currents in the telegraph wires, a phenomenon called earth currents that was interfering with communications. Modern measurements of Cornish granite using sensitive voltmeters show persistent voltage differences of 0.05 to 0.3 volts between different points on the same rock formation. The voltage is weak but consistent, maintained by the continuous radioactive decay occurring within the stone. The electrical activity is strongest during wet weather, when moisture provides better conductivity. During dry periods, the voltage can still be measured, but the available current is much lower because there's no conductive path for charge to flow. What's particularly interesting about the Cornish granite is the time scale. The radioactive elements in the rock have half-lives of millions to billions of years. The uranium-238 half-life is 4.5 billion years, and thorium-232's half-life is 14 billion years. These stones have been generating electrical activity for geological time spans and will continue for millions of years into the future. Some researchers have investigated whether the ancient tin miners who worked Cornwall's mines for thousands of years might have noticed electrical effects from the rocks. There's no clear evidence, but some mining folklore describes certain rocks as having spirit or unusual properties, descriptions that could potentially relate to electrical sensations. Dr. Richard Haworth, a British geophysicist who studied Cornish granite in the 1970s, proposed that similar radioactive granite formations worldwide might generate sufficient electrical activity to affect local atmospheric electricity and possibly contribute to certain weather phenomena, though this hypothesis remains unproven. The Cornish granite formations remain popular with geologists and rock collectors. While the electrical properties aren't dangerous, the radioactivity levels are low and the voltage generation is weak. They represent a fascinating example of how natural radioactivity can create persistent electrical phenomena in rocks. Black sand beaches of Iceland. Iceland's volcanic black sand beaches, particularly those near Reynisfjara and Vik, contain minerals that generate measurable electrical activity. The black sand is primarily composed of basalt fragments, magnetite, and other iron-rich minerals eroded from Iceland's volcanic rocks. The electrical generation mechanism here is different from the previous examples. It involves what's called the triboelectric effect, the generation of electrical charge through friction. When wind blows across the black sand beaches, the sand grains rub against each other. Because the grains are made of different minerals with varying electrical properties, this friction transfers electrons from one mineral to another, creating static charge. Under typical conditions, this charge would dissipate quickly, but Iceland's black sand beaches have unique properties that allow charge to accumulate and persist. The sand contains high concentrations of magnetite, which is semiconducting and can retain electrical charge longer than typical sand. Additionally, the constant wind and wave action continuously generates new charge through friction. Researchers from the University of Iceland measured electrical potentials in the black sand in 2010 and found persistent voltage differences of 0.5 to 1.5 volts between different areas of the same beach. The voltage was higher during windy conditions and lower during calm weather, confirming the triboelectric mechanism. But there's another factor contributing to the electrical activity: The magnetite in the sand is magnetic, and as it moves and tumbles in wind and waves, it moves through Earth's magnetic field. This movement induces tiny electrical currents in the individual grains through electromagnetic induction, the same principle used in electrical generators. The induced currents in individual sand grains are infinitesimally small. But across an entire beach with billions of magnetic sand grains all moving and tumbling, the cumulative effect is measurable electrical activity in the sand as a whole. Visitors to Iceland's black sand beaches sometimes report unusual sensations, tingling feelings, or the sense that the sand is alive. While these sensations could be imaginary or caused by other factors, it's possible that some people are sensitive enough to detect the electrical activity in the sand, particularly during very windy conditions when the triboelectric generation is at its peak. The electrical properties of volcanic black sand aren't unique to Iceland. Similar sands in Hawaii, New Zealand, and other volcanic regions likely have comparable properties. But Iceland's beaches have been most extensively studied due to their accessibility and the country's strong geological research tradition. The black sand's electrical generation is strongest in the surf zone, where sand is constantly agitated by waves. Researchers have measured voltage gradients, voltage differences per unit distance, exceeding 10 volts per meter in the active surf zone during storms, though this voltage is distributed across the sand and not easily harvestable. Piezoelectric coastal rocks. Along certain coastlines worldwide, particularly in regions with granite or quartz-rich rocks, the constant pounding of waves generates persistent electrical activity through piezoelectric effects. This phenomenon has been documented most extensively along the coasts of Brittany, France, and the Galician coast of Spain. The mechanism is straightforward. Quartz-bearing rocks are piezoelectric, meaning they generate voltage when mechanically stressed. Ocean waves striking the coast create enormous mechanical forces, thousands of pounds per square foot during large swells. These impacts compress the rocks, and if the rocks contain sufficient quartz, piezoelectric voltage is generated. The voltage generated by a single wave impact is transient. It appears during the compression and dissipates afterward, but on coasts exposed to constant wave action, the rocks are being compressed continuously, one wave after another, hour after hour, day after day. While each individual voltage pulse is brief, the continuous succession of pulses creates a persistent electrical field in and around the rocks. In 1997, researchers from the University of Rennes in France measured the electrical activity in granite sea cliffs along the Brittany coast. They found that the rocks maintained measurable voltage differences of 8.2 to 0.6 volts between different points on the cliff face, and that this voltage fluctuated with wave action, increasing during high seas and decreasing during calm conditions. What makes this phenomenon particularly interesting is its potential energy significance. The ocean's mechanical energy is enormous, and if piezoelectric generation from wave impacts could be efficiently harvested, it could represent a renewable energy source. However, the distributed nature of the phenomenon, voltage generated across entire cliff faces rather than concentrated at points, makes energy collection challenging. Some researchers have proposed that the piezoelectric generation in coastal rocks might contribute to rock weathering and erosion. The electrical fields generated could accelerate electrochemical reactions at the rock surface, potentially accelerating breakdown. This remains a hypothesis, but if true, it would mean that the electrical properties of rocks contribute to shaping coastlines. Ancient peoples living on quartz-rich coasts might have observed unusual phenomena related to this electrical generation. Some coastal legends describe living stones or rocks with special properties near the sea. Whether these legends relate to electrical phenomena is speculative, but the possibility exists. The piezoelectric generation in coastal rocks continues everywhere waves strike quartz-bearing formations. It's a constant, ongoing geological electrical phenomenon driven by ocean energy, converting mechanical wave energy into electrical potential through the crystalline structure of rock. Deep mine sulfide deposits. In deep metal mines worldwide, particularly those extracting copper, zinc, and lead from sulfide ores, miners have long reported unusual electrical phenomena. In some mines, electrical equipment malfunctions. Workers report tingling sensations when touching certain rock surfaces, and unexplained electrical readings appear on monitoring equipment. Investigation has revealed that sulfide ore deposits, particularly when wet, can generate substantial electrical currents through electrochemical processes. The mechanism is complex, but involves the oxidation of sulfide minerals in the presence of water and oxygen. Sulfide minerals like pyrite, iron sulfide, chalcopyrite, copper iron sulfide, and sphalerite, zinc sulfide, are chemically reactive. When exposed to water and dissolved oxygen, they undergo oxidation reactions that release electrons. If different sulfide minerals with different electrochemical properties are in contact through moisture, electrical current flows between them, creating natural galvanic cells. In the Sudbury Basin mines of Ontario, Canada, some of the world's largest nickel-copper sulfide deposits are extracted. In 2005, mining engineers documented electrical currents of up to 2 volts flowing through certain ore bodies when saturated with groundwater. These currents were strong enough to cause noticeable electrical shocks if workers touched the wet ore with bare hands. The electrical generation in sulfide deposits isn't just a curiosity, it has practical implications. The electrochemical reactions that generate electricity also produce sulfuric acid as a byproduct. This acid can accelerate corrosion of mining equipment, degrade rock stability, and create environmental challenges when acid mine drainage reaches surface water. Researchers from the Colorado School of Mines studied electrical generation in sulfide deposits in the 1980s and found that the process is self-sustaining and can continue for decades. As long as water and oxygen are present, the sulfide minerals will oxidize, generate electricity, and produce acid. What makes sulfide deposit electrical generation particularly powerful is the large surface area involved. In an ore body extending over hundreds of meters, with fractures and pores throughout, there's enormous surface area where electrochemical reactions can occur simultaneously. The cumulative electrical generation from all these reactions can be substantial. Some mining operations have explored whether the electrical currents in sulfide deposits could be harvested for practical use. In theory, electrodes could be placed in the ore body, and the natural electrical generation could provide power. However, the corrosive environment and the distributed nature of the current sources make this technically challenging. The electrical activity in sulfide mines is ongoing wherever such ores are exposed to water and air. It's a geological phenomenon that converts chemical energy stored in sulfide minerals into electrical energy, sustained by the natural oxidation of the ores. The Tourmaline fields of Brazil and Madagascar. Tourmaline is a complex borosilicate mineral known for its unusual electrical properties. Unlike typical piezoelectric materials that generate electricity only when mechanically stressed, tourmaline is pyroelectric. It generates electrical charge in response to temperature changes, and also maintains permanent electric polarity. Large tourmaline crystal formations in Brazil and Madagascar exhibit persistent electrical fields that have been documented by mineralogists for over a century. These fields aren't generated by external energy sources. They're intrinsic properties of the crystal structure. Tourmaline crystals have asymmetric crystalline structure with different compositions at opposite ends. This asymmetry creates a permanent electric dipole. One end of the crystal is permanently slightly positive, the other slightly negative. The voltage difference between the two ends can be measured and typically ranges from 0.1 to 0.8 volts for large natural crystals. What makes tourmaline's electrical properties remarkable is their persistence. Unlike batteries that discharge or piezoelectric crystals that only generate voltage when stressed, tourmaline's electric polarity is permanent. It's a result of the crystal structure itself and remains as long as the crystal exists. The pyroelectric property adds another dimension. When tourmaline is heated or cooled, it generates additional electrical charge. The temperature change causes the crystal lattice to expand or contract slightly, altering the degree of asymmetry and changing the surface charge. This generates measurable voltage changes in response to temperature fluctuations. In the 1880s, Pierre and Jacques Curie, who also discovered piezoelectricity in quartz, studied tourmaline's electrical properties extensively. They documented that large tourmaline crystals maintained measurable voltage indefinitely, and that this voltage increased when the crystals were heated. Brazilian tourmaline deposits, particularly those in Minas Gerais, include massive crystals, some weighing several kilograms. These large crystals exhibit electrical properties strong enough to attract dust and small particles, similar to static electricity. Miners have long known that tourmaline crystals should be handled carefully because they can create uncomfortable electrical sensations. Madagascar tourmaline deposits, particularly those in the Antsirabe region, include unusual tourmaline varieties with especially strong electrical properties. Some crystals show voltage differences exceeding 1 volt between their ends when heated, making them effectively natural thermoelectric generators. The permanent electrical properties of tourmaline have made it valuable for certain technical applications. Before synthetic materials became available, tourmaline crystals were used in pressure gauges and other instruments requiring stable electrical properties. Today, tourmaline is still valued for specialized applications where its unique electrical characteristics provide advantages. What makes tourmaline particularly interesting for our topic is that it demonstrates how crystal structure alone, without external energy sources or chemical reactions, can create persistent electrical phenomena. The stones literally generate voltage simply by existing, maintained by the fundamental arrangement of atoms in their structure. Electrified gold veins of the Witwatersrand. The Witwatersrand Basin in South Africa contains one of the world's largest gold deposits. These deposits are found in ancient sedimentary formations called reefs, and miners extracting gold from these reefs have documented unusual electrical phenomena for over a century. In the 1960s, mining engineers noticed that certain gold-bearing reef formations maintained measurable electrical potentials. When separated electrodes were placed in different parts of the same reef, voltage differences of 0.3 to 1.2 volts were measured, and these voltages persisted over months of observation. The mechanism appears to involve the unique composition of the Witwatersrand reefs. The gold occurs alongside pyrite, iron sulfide, uranium minerals, and carbon-rich compounds in a complex assemblage. When groundwater permeates these reefs, multiple simultaneous electrochemical reactions occur. The pyrite undergoes oxidation, generating electrons. The uranium minerals provide low-level radioactivity that ionizes water and rock, creating ions that can carry current. The gold itself, being an excellent electrical conductor, provides pathways for current flow. The carbon compounds participate in redox reactions. The result is a complex electrochemical system generating persistent electrical activity. Researchers from the University of the Witwatersrand studied the phenomenon in the 1990s and found that the electrical generation was strongest in sections of reef with high uranium content. The radioactivity appeared to be enhancing and sustaining the electrochemical reactions, providing continuous energy input to the system. What makes the Witwatersrand electrical generation particularly significant is its geological age. These gold deposits formed approximately 2.7 billion years ago. The uranium minerals began radioactive decay immediately and have been decaying ever since. This means these rocks have been generating electrical activity for billions of years, among the oldest continuous electrical generators on Earth. Some researchers have speculated whether the electrical activity in the reefs might have influenced gold deposition. Gold is mobile in certain chemical conditions and can be transported as ions in solution. Electrical fields could potentially influence where gold ions precipitate out of solution, possibly contributing to the concentration of gold in specific locations within the reefs. This hypothesis remains controversial and unproven, but it raises an interesting question. Might the electrical properties of rocks influence ore formation? Could natural geological electrical phenomena contribute to concentrating valuable minerals in specific locations? The Witwatersrand gold mines continue to operate, and the electrical phenomena remain documented. Modern deep-level mines extract gold from depths exceeding 3 kilometers, where the electrical properties of the rocks continue to be observed and must be accounted for in mining operations. These 10 cases demonstrate that electrical generation by rocks and minerals is far more common than generally recognized. From the Telluric currents in Sweden's Iron Mountain to tourmaline's permanent electric dipoles, from sulfide ore deposits creating natural batteries to quartz crystals generating piezoelectric voltage from internal stress, stones around the world continuously produce measurable electrical activity. The mechanisms vary: electrochemical reactions, piezoelectric effects, radioactive decay creating ionization, thermoelectric generation from temperature differences, triboelectric charging from friction, and permanent electric polarization in crystalline structures. What unites these phenomena is that they convert other forms of energy, chemical, mechanical, thermal, nuclear, into electricity through the properties of minerals and rocks. Most of these electrical phenomena are weak by modern standards, fractions of a volt, currents measured in microamperes, but they're persistent, continuous, and in some cases have been ongoing for millions or billions of years. They represent natural electrical generation that predates human civilization and will continue long after we're gone. Could ancient peoples have detected these phenomena? Possibly. Human bodies can sense electrical fields under certain conditions. Several of these formations produce strong enough electrical activity that touching them when wet creates noticeable sensations. Whether ancient cultures recognized these properties and attributed special significance to electrically active stones remains speculative but intriguing. What's certain is that Earth's geology includes electrical phenomena we're still discovering and studying. These stones that generate electricity reveal that the boundary between geology and electricity isn't as clear as we might assume. Rocks aren't inert. They're dynamic systems where chemistry, physics, and geology intersect to create phenomena, including persistent electrical generation, that challenges our assumptions about what stones can do.